Um, okay, so, well, thanks for the introduction. As we heard, I'm a professor at the University of Oxford. I'm speaking to you from my college office here in Oxford. And what I'm going to talk to you about is exactly what Lars mentioned, the idea of connected artificial intelligence, the idea of artificial intelligence systems that can talk to one another. And what I'm going to do is I'm going to talk to you about where that idea came from. So the first thing I'm going to do is I'm going to talk through some trends which have been ongoing in computing really throughout the history of computing. And the first trend, if you go back for the last 50 years, and every year you will have seen this trend evident in computing, and it's a trend towards ubiquity. And ubiquity, when you say something is ubiquitous, you just mean it's everywhere. And when we talk about ubiquitous computing, that's what we mean. We mean it's computer systems everywhere, computer systems that are embedded in ever more devices and in ever more places. And this is possible because of something you may well have heard of, Moore's law. And Moore's law, basically, there are many different formulations of it, but basically what it says is chips, microprocessor chips, get smaller and smaller each year, and they get cheaper and they require less power. And the upshot of that is that you can start to do things with computer processors. You can start to put them into devices and into places that you couldn't have done previously. And Moore's law has been a pretty good, it's held pretty well for the last 50 years or so. It's kind of slipping a little bit now, but nevertheless, for the foreseeable future, computer processors are going to continue to get smaller and cheaper and require less power. Okay, so computer processors everywhere, in everything we build. And the second trend is towards interconnection. So when I was a student in the 1980s, my lecturers told me, these idea of networked systems, we did lectures on them, the idea of computer systems that were connected to one another via a network like the internet. And they said, well, these things are difficult to build, but don't worry, because you're never going to encounter one. Well, boy, they got that wrong. And now we realize that actually interconnected systems that can talk to one another, this is absolutely the norm in computing. And the advent of the smartphone and having computers that are with us 24 hours a day, that are seamlessly connected to the internet, that's only a decade old, that idea. And think about how much that idea has changed the world over the last decade. So we've got computer processors absolutely everywhere, and they're interconnected. They can all communicate with one another. So the next trend is towards delegation. So what do I mean by delegation? Well, what I mean is we delegate ever more tasks to these computers. We hand over more and more control of our lives. We get the computers to do more and more things for us on our behalf. That's the trend towards delegation. And when I was a student in the 1980s, the big debate at the time was about fly-by-wire aircraft, the idea about having aircraft with computerized control systems where humans were no longer in the loop, no longer directly controlling the aircraft, and it was very contentious at the time. And the debate we're seeing at the moment is around driverless cars. And there are lots of arguments for driverless cars, mostly around safety and efficiency and so on. But some people are concerned about that. But this is a classic example of what we're doing is handing over control to the computer and letting the computer take control. And whether it happens this decade or a couple of decades' time, driverless cars for sure will happen. Okay. Ubiquity, computer processors everywhere, interconnection, they're all connected to one another, they can talk to one another. We delegate ever more things to them. Human orientation is the next trend. And what that means is the way that we interact with these devices gets ever more like the way that we interact with people. And the beautiful example of this at the moment is Alexa and Siri and Cortana. And I'm going to come back and talk about those in a moment. But the point is you talk to them, you give them instructions in natural language, in languages like English or French or whatever. And that's very different to the way that you used to interact with computers, where you would need experts who'd been trained in using the computers to be able to interact with them. So the way that we interact with these devices gets ever more like the way that we interact with people. And then finally, intelligence. So over the last 10 years or so, we've seen a huge growth in artificial intelligence where now we can do things with AI that were unimaginable a couple of decades ago. And that trend is going to continue. So these trends then, computer processors everywhere, ever more interconnected, to which we delegate more and more, to which the way that we interact with them is ever more like the way that we interact with people, and that are getting smarter and smarter. So those trends have been evident for the last 50 years, and I think it's a very safe bet that they will continue. So where is this taking us? Well, there's the general space in which it's taking us towards ubiquitous interconnected devices that are ever more intelligent and so on. That's clear, but there are lots of different versions of that future. There are lots of different trends that have come up over the last 15 years, which have pointed towards bits of that. So cloud computing points towards ubiquitous computing and connected computing. Ubiquitous computing itself, this is a field in computing, and it's all concerned with populating our environment with devices that sense us and watch us as we go about our lives. The Internet of Things, the idea that your coffee machine is connected to the internet, you know, that your fridge is connected to the internet, that your washing machine is, and so on. That's the Internet of Things. These are all versions of, they're all manifestations of that dream. They're all possible because of those trends. But the one that I want to focus on is the final one. And this is a trend towards multi-agent systems. And for AI researchers, this is the most evident manifestation of that dream. So if we think about AI systems that are ubiquitous, that are interconnected, that act autonomously on our behalf, that we delegate things to, that are intelligent, and that we interact and program with them like with human-like metaphors, in AI, where that takes us to is what we call agents. And an AI program which acts on your behalf and cooperates with other AI programs that has some degree of intelligence and which you interact with via human-like metaphors. That's what we mean when we talk about agents in AI. So this is a very old dream, and in fact, Lars mentioned I've been working in AI since the late 1980s, and this is what I've been working on. I've been working on agents, and so we had this dream back in the late 1980s, but we didn't have the technology to make it feasible. Computer processing power and the science of AI was just not sufficiently advanced to make that feasible. But it is feasible now. And each of you carry around with you a manifestation of that dream. So Siri and Alexa and Cortana, these are all agents. They're AI programs which you interact with via a natural language with a very human-like way of interacting with them. And those interfaces are a bit clunky now, but they will carry on getting better and better over time. They are systems that have some degree of autonomy, you know, that you ask them to book a taxi for you and you just expect it to go out and do that. And they have sort of AI embedded with them, and they're seamlessly connected to the internet. So bringing all of those trends together into these, what we call software agents. Now, going beyond the agent in your pocket, they could be robots. They could be household robots. We're still some way, I think, from making that a reality. They could be vacuum cleaners like Roomba, or they could be driverless cars, your Tesla, and so on. Or they could just be software. But where we're going to get to at some point in the near future, and this is the real dream of multi-agent systems, is the idea of Siri talking to Siri. So at the moment, when I ask Siri to book me a meeting, book a meeting with Janine, for example, what Siri does is calls up Janine and speaks to Janine. Well, technology's not quite there to do that, but it will be there to do that pretty soon. But actually, this makes no sense. Why doesn't my Siri talk directly to Janine's Siri? Why don't we let the software agents work it out amongst themselves and arrange the meeting amongst themselves? And maybe Janine's software agent says, no, I don't want a meeting with Michael, and there's no meeting happens. But the point is, why isn't interacting agents more of a reality today? And that's the dream where we want to take multi-agent systems. Now, there are some applications of multi-agent system technology where you have AI systems that are interacting with other AI systems that are in use today. And so high-frequency algorithmic trading programs are exactly that. So what are high-frequency algorithmic trading programs? So on the global markets, the global money markets, the stock markets, and so on, well, basically, humans no longer do the buying and selling. So the old idea that you have of a stock market, where you have lots of people waving a piece of paper in the air to try to buy some stock or some currency and so on, that's actually very, very out of date. It's all automated. And actually, by and large, humans are out of the loop. It's computer programs, agents, that are doing the buying and selling. And they're doing the buying and selling on timescales which are really unimaginable. They're on microsecond timescales, and there is a kind of an arms race amongst the developers of these trading programs to make them even faster, because even tiny speed ups in the speed of your trading program can bring you huge advantages. If you spot something which is happening on the Hong Kong Stock Exchange, momentarily before everybody else on the London Stock Exchange spots it, you've got an advantage there. You've got a trading advantage which you can exploit to make money. So trading on the global markets is by and large done by what we call high frequency or algorithmic traders that are buying and selling autonomously, and they are interacting with other agents to buy and sell. That's exactly what they're doing, and they're doing that interaction through the global marketplaces. So to make that vision work, your agent needs to know your preferences. This is a big challenge. It needs to know what you like. So the dream that we have is that Siri is going to be like a human secretary. It's going to be something like, a human secretary where you can say, book me a flight to Paris, book me a weekend in Paris, and they will go away and they will book you a flight and a taxi to the airport, and they will book you a hotel in Paris and so on, and maybe book you into restaurants for dinners and so on. But to make that work, they need to know your preferences. They need to know, for example, that you don't like flying business class on short haul flights because it's not cost effective, and you don't like this particular hotel chain. I won't name any hotel chains, but you get the idea. They need to know your preferences. So the metaphor is just as a human assistant would work with you. The idea is that the agent will work with you. And to make that work, it would need to know your preferences. But more than that, and Lars mentioned this in the introduction, if agents are going to interact with one another, then they need social skills. They need the ability to cooperate, coordinate, and negotiate with other agents. They need the ability to cooperate, coordinate, and negotiate with other agents. And what I'm going to do in the talk is explain exactly what those social skills look like and how we might go about building agents with those social skills. Okay, so these are social skills, and historically, one of the slightly odd things about artificial intelligence is for roughly half of its history, AI just didn't think about these kind of skills at all. The kind of things that AI was concerned with were things like what we call problem solving and planning, which by and large are things that an AI system does on its own. And the issues of what happened when AI systems talk to one another were largely ignored by the community. But my research has been solely concerned around building AI systems that have those skills, the ability to cooperate, coordinate, and negotiate. Okay, so let's talk through what I mean by cooperation, coordination, and negotiation. So here's a picture to illustrate this. So one big research area within artificial intelligence at the moment is what's called disaster robotics. So the idea, this is prompted by a couple of historical natural disasters. One was the Kobe earthquake in the 1996, I think it was, terrible earthquake that happened in Japan that killed thousands of people. The other was the tsunami in Japan in 2011, and the subsequent disaster at the Fukushima nuclear power plants. So if you go to Fukushima, one of the problems was the place was so radioactive that human explorers couldn't possibly go in. It was just far too dangerous. There weren't any sort of lead costumes that you could wear that were going to make it safe enough for human explorers to go in and explore what had happened inside those reactors after the tsunami. So it's a very natural idea. What you really want is robots to go in there and do that. And in many other scenarios as well, this has happened. It even happened after the terrorist attacks of September 11th, 2001. There were some prototype robotic disaster robots that were sent in to explore the ruins of the Twin Towers in New York and look for survivors or human remains. So the dream of disaster robotics is sort of illustrated in this slide. So the idea is some disaster like an earthquake has taken place, and a building is partially collapsed and there are fires broken out and it's too dangerous for humans to go in and explore. So what you do is you send in some robots, and those robots go off and they locate the humans. Maybe they communicate with them directly if the humans are capable of talking to them, or otherwise they make some kind of judgment. To make this work, the robots have to behave as a team. The robots need to cooperate in order to locate the survivors, prioritize them, potentially treat them, and maybe even rescue them. Now, I emphasize, we're not at that future yet, but there are many prototype systems that are out there around about doing that kind of thing. So what does working as a team mean? Well, it means being able to know when is the right time to share information. So when should a robot share information about what it's found with other robots, for example, is a very, very natural problem. And knowing, not bombarding other robots with information, but actually knowing this robot needs to know this at this particular time. This is the right time to share that information. But also it means sharing tasks. So it's very natural to think, just as in human teams, you have humans who are specialized in various different tasks. It's very natural to think of in robot teams that you have robots with various different specialized capabilities. So you can imagine at some future point, you have a robot which has got which is equipped with a medical kit to deal with burns, and another one to deal with compression wounds, and so on and so on and so forth. I emphasize this vision is still at a very early stage. So working as a team is about cooperating, just as a human team would do. And two of the most fundamental things that you want to do there are share information and to share tasks. So what we do in my community is we build protocols, we build techniques that these agents can use, because they're physically embodied agents, they're robots, and we build protocols that these robots can use in order to be able to cooperate. Okay, what about coordination? Well, what is coordination? Coordination happens when, if you remember back to the days when when, for example, we would all be in a big lecture theatre together, or maybe all in a big concert hall, and the lecture ends or the concert ends and we all head towards the exit. And there you've got what we call a shared resource, the exit, and maybe it can fit, let's just assume it can only fit one person at any given time. Well, somehow what we manage to do is to coordinate. And what I mean by coordination there is we manage our activities so that we use this shared resource safely, so that we're not all piling in to this exit at the same time. Because if we do that, then we're never going to be able to get out safely. That's what coordination is all about. It's about managing the dependencies between our actions. The dependencies, the relationships that my action has to your actions. And in this case, in the case of the exit, right, if we both try and exit at the same time, then there's a dependency between those, which means that they mutually will prevent each other from being successful. So the kinds of relationships that you need to think about, the kinds of dependencies that you need to think about, they can be positive. So something I do can enable something that you do, or it can promote something that you do. That is, I can do an action which helps you subsequently, but they can also be negative dependencies. So I can do an action which then prevents you from carrying out your actions or impedes you in causing other agents. Now, the interesting thing about coordination is that to make that happen, you have to have agents that can reason or model other agents. So this is a scenario. This is just a concrete scenario, variation of the one that I talked about. So we've got two robots in a warehouse, and the robot in the top left just wants to visit the bottom right location and return. Maybe it's taking a package down there and returning, and then taking another package and returning, and then taking another package and returning. The robot in the bottom right wants to visit the top left and then return, and then visit the top left, and so on. And this scenario is very real. The people that we're working with are thinking about deploying multiple robots in shared warehouses, right? And so these robots are owned by different organizations. So they can't, they're not programmed by the same organization. So these robots need to be able to predict, to model and understand each other's actions in order to prevent them crashing when they try to pass through the door in the middle there. That's what coordination would mean in this particular setting. So next, negotiation. So what do I mean by negotiation? I mean negotiation very much like it occurs in the real world. So here, what we've got, this little graph thing on the right-hand side, this is a transport network, and each of the circles is a location. So the circle 1, 2, 3 across the top, these are all different locations. Think about these as being intersections on a road junction. These are all different locations. And the numbers on the edges that connect them, these are distances. It's the amount of time it takes to use that particular connection. So to go directly from location 1 to location 4 is going to take you 12 minutes. To go from location 1 to location 2 is going to take you 5 minutes. Okay. Now, Company A and Company B are both located in location 1, right? So imagine again that this is some dispatch warehouse. And Company A needs to send out packages, like Amazon packages or whatever, to locations 5, 3, 8, and 9, while Company B needs to drop packages off at locations 4, 5, 3, and 9. Well, the standard sort of AI way of thinking about this is you find what's called the shortest path, the shortest route that will get you through those things, and then you traverse the network accordingly. But actually, here, they can benefit by reallocating their duties. So you notice that they both need to service location 5, they both need to service location 3. Well, actually, only one of them needs to go to location 5 and only one of them needs to go to location 3. So what they can do is they can just rearrange their parcels. Look, you take my parcel that needs to go to location 5 and you visit location 5, and I'll take your parcel that needs to go to location 3. So I will need to visit location 3. So a possible solution is that Company A visits locations 5, 3, and 8, and Company B visits locations 4 and 9. Okay, so that seems like a reasonably sensible solution. Of course, there are bad solutions to this. So one possibility is that Company A visits all of the locations and Company B does nothing. So this is not good for Company A. So the process via which you find a fair allocation is called negotiation. And again, what we've developed in multi-agent systems is protocols, techniques that will allow us to do that, so that you can say, this company needs to visit this locations, this company needs to visit these locations, and they will negotiate and they will find an allocation. And here's the really cute thing. We can do it in such a way that we never get a scenario like the bad scenario that we had previously, where A does everything and B does nothing, in which case Company A has been ripped off. We can design protocols which are, in a precise sense, fair. Okay, so that's what negotiation is. And there are tons of applications to multi-agent systems using the kind of techniques that I've talked about. So I already mentioned the idea of meeting scheduling. I wish somebody would just do this, by the way, so that I could just say, book a meeting, Siri, book a meeting with Janine, and that meeting would just appear in my diary using my preferences. So knowing that I don't like meeting at 8 o'clock in the morning and so on. But there are many other examples as well. Multi-robot warehouses, I've already talked about. Agent-based simulation, agent-based workflow. These are all examples. What is agent-based workflow? A lot of us spend our working lives on a website where we're clicking through and entering data in a form and so on. And then I press a submit button and it goes off to somebody else in my organization for their approval. And then they fill out a form and press submit and it goes to somebody else. Having agents being able to manage that, a lot of that mundane, dull, boring stuff would be a tremendously useful thing to be able to have. So there are many other examples. Connected vehicles. So Tesla and other companies are demonstrating driverless car technology. It's still at relatively primitive levels compared to what we would ideally like, what's called level 5 autonomy. At the moment, we're at level 2, about level 2.5, I would say, in a Tesla, somewhere between 2 and 3 maybe. But when we've got driverless cars, the next step is what we call connected vehicles. And the idea is that your car will start to talk to other cars on the road. And maybe it will negotiate. You want to overtake? Well, fine, I'll let you overtake me if you pay me. You make some kind of micro payment. You're in a hurry, I'm not, so fine. You pay me 10 cents and I will let you overtake. So you can imagine the cars actually negotiating about overtaking or using a busy road intersection and so on. That's the dream of connected vehicles. And, we can imagine fleets of lorries on the roads making very efficient use of limited transport, limited capacity transport networks and so on. Okay, so the last thing I want to talk about is to hint about some of the research that we do. So I've painted you a picture of multi-agent systems, and basically the take-home message is what you need to think about: Siri talking to Siri, or Siri talking to Alexa. So I want to arrange a meeting with Janine. I just say to my Siri, Siri, book a meeting with Janine. Siri talks to Janine's Siri. They get that thing in the diary. To be able to do that kind of thing and unleash the applications and services that promises, these agents need to have social skills, the ability to cooperate, to work with others as a team, to coordinate, to manage the interdependencies between their activities, the ability to negotiate. Okay, but I've already mentioned that we do have multi-agent systems in the world right now, and automated trading programs are one example. But actually what they demonstrate is that kind of system is very often inherently unstable. So back in the 1980s, just after the computerization of the stock markets, where buying and selling of stocks was done now via a computer network, it was called the Big Bang. We saw a market crash, and that market crash unfolded over a period of days. And it was a very serious event in the 1980s economy. But if you step forward through time to 6th of May 2010, we saw what's called the flash crash. And over a 30-minute period, the Dow Jones Industrial Average in the United States collapsed, and it lost over $1 trillion. And some major shares very briefly traded at about a penny a share. Very briefly, for very short timescales. And then something weird happened. The markets bounced back, and 20 minutes later, they were at where they'd nearly at where they'd been before. This is what it looked like. This is the Dow Jones Industrial Average on 6th May 2010. And there you can see the flash crash. And what you have to understand is the time to go from 10,600 down to now 9,900 is about 15 minutes. It was so fast and so unprecedented that humans didn't have time to intervene. They had no conception of what was going on. It was just this system was operating on a timescale which was unimaginable for them. But then you see over the next 15 minutes, it starts to bounce back. So what we do in our work is what we would like to do is to understand what kinds of systems might cause flash crashes and how can we prevent them. But more generally than that, not just flash crashes, but kind of bad scenarios in your multi-robot warehouse, or bad scenarios when your Siri is talking to my Siri. And we've got two approaches to doing this. The first is the idea is that we treat the flash crash as a bug. Right, so when I talk about a bug, I mean something that's wrong in a computer program, and we've been trying to develop techniques so that computer programs are free of bugs. We've been doing that for decades. So can we use the same ideas if we treat the flash crash as a bug to try to understand when it can occur, and to engineer systems, these multi-agent systems that are free of those bugs? The second approach is what we do is we simulate the system, and we've adopted that approach as well. And so I'll say a little bit more about these two approaches. So the first approach, treating the instabilities in a system as a bug, and trying to find out when those bugs are going to hit. What we do in our work, we call this rational verification. What we do is we model a system like a trading system, and we assume that the components of that system are what are called rational actors. They've got their preferences, which I give them. And in trading agents, the preferences are usually very simple. They're like, make as much money as possible. And we assume that these agents, these AI programs, are going to act rationally to try to bring these preferences about. And to understand these systems, we use ideas from game theory. And game theory derives from economics, and it's concerned with understanding strategic interactions between individuals. The individuals in this question are our software agents. It's Siri and Alexa and Cortana. And the key idea is that some events that could in principle happen won't occur if the agents act rationally. So we can distinguish between something which could happen in principle and something which could happen assuming the agents act rationally. And we've got two key concepts, what are called, and these concepts are named after John Forbes Nash, who was the inventor of one of the key ideas that we use, which is called a Nash equilibrium. And they're called Nash reachability and Nash invariance. And what Nash reachability means is that this thing could happen assuming the agents act rationally. And technically what that means, according to this concept of a Nash equilibrium, which is a central concept in game theory. We don't have time to go into the details. Nash invariance means that something is inevitable under the assumption that the agents act rationally. And so what we have is we have a system called Eve. You can even try it out, eve.cs.ox.ac.uk. What it does is it takes as input, this is the system that we're modeling in the top left. This is our trading system, for example. We've got a query about the system. So think of this query in the middle as being something like a flash crash will happen. We've got the player preferences, which in the trading scenario will just be make as much money as possible. And what our system does, the Eve system will do, is it will find out whether that thing could happen under the assumption that the agents act rationally. So that's rational verification. Going back to our robot scenario, in this particular scenario, if both of the robots use that approach, then they can find a game theoretic solution where they both get their goal achieved. And actually, there's infinitely many solutions to this. But basically, what you can think about is the robot taking into account the fact that the other robot wants to get his goal achieved. The one in the top left can just get out of the way, let the robot in the bottom right come in, and then move down to the bottom right. And then he gets out of the way and lets the other robot come back, and so on. So using this approach, taking into account each other's preferences, they can find satisfactory solutions. There's solutions that are satisfactory for both of them. Finally, pretty much the last thing I'm going to say is about agent-based modeling. So this is work that we've done where with financial systems, they're very, very large, and trying to find bugs in them in the way that I've described is just not feasible for all sorts of reasons. So what we do is we simulate them. We actually run simulations using real world data. And the kind of things that we look for, we use real world data where we model actual banks and their actual loans that have occurred in these banks and so on. And we look at what the techniques that the markets have introduced, things like limit up, limit down, that they introduced to try to prevent flash crashes. So limit up, limit down means if a stock drops 5% in 5 minutes, you stop trading on that stock for 5 minutes. The circuit breaker, if the Standard & Poor index drops 7%, then you freeze everything for 15 minutes. If it drops 20%, then you freeze everything for the day. And these are interventions which are used in the marketplace. And what we've looked at is, do they actually work to prevent flash crashes? And the answer is no, not really, actually. But the detail is a bit more complicated than that. But anyway, the point about agent-based modeling is that what you're doing is you're actually modeling down at the level of individual traders and banks, the actual individuals that are buying and selling. So those become the agents which are interacting with each other in a simulation. And we run these simulations many times with lots and lots of real world data to explore their dynamics and find out when flash crashes can happen. Okay, and this is just to say this is possible now. It's the simulations that we use involve millions of agents, and it's really possible now because we can get the data. So since the financial crisis of 2008, banks and similar organizations have been required to file lots of data about the loans that they have and so on. And we can scrape that from the web. So we've got data, but also it takes a lot of compute power, and we can do these simulations now with large scale compute power. This is our PhD student, James Paulin. He looked at the causes of flash crashes, and his simulation involved millions of agents and lots of real world data. And he had some slightly startling findings in some cases. I'm not going to go into details, but these are some of the things that he discovered about flash crashes and how flash crashes can be propagated from one asset, from one stock being distressed that is going down to another stock being distressed and going down. Those are the kind of questions that he looked at.